So there's the Earth. It's really big. And yet if you get far enough away, it's really small. So in the early 90s, I worked with Vice President Gore on a program to develop a program called GLOBE. We had a lot of discussions. In this room are people hugely well informed. Esri has been a huge positive for all of us who love maps and love to try to understand the world, but there's coming on 8 billion people on Earth. And something that I mulled over after that tour in the White House was done is, how do you affect the 8 billion? That was really something the vice president was trying to figure out too. And one day I got to thinking about, basically people learn visually. So if we look at the Earth, we see it's complicated. There's probably enough ocean there to satisfy Sylvia, but I'm not sure. But how do people understand things like climate change, or weather, or biology, or chemistry? So my idea was, they've got to visualize it. So in 1995, I got a beach ball. That isn't really me. He has more hair and I have a better shirt. So I painted the beach ball white. I put it in my garage, made my wife park her car outside for a while. And I got 2 video projectors. I just wanted to prove that we could sync up visual images in a very striking way. Then, fast forward, there were a couple of years where I thought about it, looked at textbooks on optics and said, what is the right way to do this? And I came up with the idea of a 6-foot sphere for museums, a personal sphere, where people could walk up to the Earth and they could see climate change, and they could see the biology, and they could see the chemistry, and how the Earth is going to change. So I was fortunate to be head of a big NOAA lab, Earth System Research Lab in Boulder, Colorado. And so life was easy enough. All I had to do was convince people that we should build it. So we made this artist concept of what we wanted to see in museums. And I took it to NOAA. You heard a lot about NOAA from Joe Pica, and they were very positive. They said, we are oceans and atmosphere. Let's show the world, let's educate. Besides that, we'll steal a march on NASA. So NOAA funded the development of science on a sphere. We had a lot to learn. We set it up in the basement of our research lab. We learned about syncing video projectors. We learned about how to build a really light and strong carbon fiber sphere. And voila, we had a very beautiful way to show what's happening to our Earth. Fast forward to 2003. President Bush's science advisor dedicates our science on a sphere, looking a whole lot like our conception, in the lobby of the Department of Commerce building. And we started to push. My idea was we wouldn't use taxpayer money. We would give it, sell it at cost, basically, to museums around the world. And fast forward a few more years, and here we have Queen Elizabeth II getting a briefing on science on a sphere. And my apologies to the British subjects in the audience, but I'll try and say what she said. Science on a sphere is the best thing I saw in America. So I hope nobody's too mad at me here. So Science on a Sphere has been around now for quite a few years. It's in 180 museums worldwide. It's seen by close to 50 million people a year. It's about a half-hour presentation, and the science is there. The word science, I put it in there for a reason. That is, we know that data is data, and that data goes into making things like displays, and it kind of goes into information, and then knowledge. People have things in their head. But ultimately, it means nothing unless there's action. And we do have a global existential emergency. And so if people can understand what's happening to our Earth, our oceans, and our atmosphere, that is the key. By the early 2020s, almost 1 billion people will have gone and heard about our planet and what's happening and how it's changing and why it's important that we do something. So Science on a Sphere, thanks to NOAA, the wonderful colleagues there, and all of us who worked on it, is making a difference. I'm now going to jump to my new job. I retired. I guess they allowed me to retire after 43 years at NOAA. And I now work for a satellite company. I guess I did want to show something of Science on a Sphere here just before I close. When we say understand the world, I think in Esri, I don't need to say much about it. Here is the sulfate and black carbon cloud, and if we watch it in motion, this is what people see. What we see is this immense effect that humans are having. I used to give Science on a Sphere presentations, and people say, well, humans can't affect the Earth. Look at that. Let's look at the biology of the Earth. This is one that people are familiar with, but it's so darn beautiful, I just can't avoid putting it up. This is marching through years where we're looking at chlorophyll, both in the ocean and the atmosphere, and you see the green roll north in the summer and come south. So life on our planet will not be the same in the future unless we take action. So now, I want to comment on my new career, which is satellites. And it's still kind of the same career because I'm looking at how can we use satellites to see the Earth better? So this is a little teeny satellite. If I thought I could have gotten through TSA, I'd have brought a little satellite, but I just didn't want to get put in jail. So this thing is the size of a wine box. Those little leaves that come out are solar panels. And just like the computer miniaturization revolution of the 80s, we're now in the satellite miniaturization revolution. So this little wine box-sized thing can literally do the same job that 1,000 balloons released from the surface do. They measure super detailed temperature and moisture. The difference is they measure them everywhere. They measure them over the ocean, over the land, over the polar regions. One little satellite. Costs matter. A satellite this can be built and run for several years for about $1 million. So it means that you can do a lot of things. I'll show you what I mean by that here in a minute. I'm not going to talk about it, but we also collect real-time data from 20 million ship observations. So the shipboard automatic identification system transmits each ship location and where it's going and so on. And just for a little interesting thing for this audience, there's also a block there where we could transmit, ocean temperature or measurements or whatever. So we have this real-time information where we get 20 million observations a day from practically, in fact, it is essentially every ship on the ocean. It turns out, who knew that some of those ships don't want to report where they are. Big surprise there. And some of them actually lie about where they are. But that's another interesting story that I won't get into. So what about these little satellites? I call it the little satellite revolution, the third satellite revolution. Geostationaries, polar orbiter are the first two. They're highly capable. In our satellite, we have a supercomputer on board, essentially. We have a global network. We get it back in real time, 15, 20 minutes. Inexpensive. They're close to Earth compared to a geostationary satellite. They're 100 times closer. And they're self-disposing. They're up at 450 kilometers. They totally burn themselves up, whether you like it or not, in 3 years, and they're gone. So what can you do in Earth observing with this kind of a satellite, which is why I came to this? Well, you can have kind of a lot of detail on the Earth. This is a network that we designed. Each one of those little dots is one of our satellites. This is not something we are building, but this is something that you could build for a relatively small fraction of the cost of a big satellite. This is 1,000 satellites looking everywhere all the time. At any point, you're basically typically in view of 10 satellites. So you can get the three-dimensional structure. You can do other things like track clouds or chemistry or measure ocean color or all kinds of possibility. Right now we do measure ice freeboard, that is the amount of ice above the surface of the geoid. And so we've got a pretty detailed measurement, and I'm going to show you a few other things that we do with these constellations. Of course, that's part of the deal. This third satellite revolution, people are going to put up not just 1,000, they're going to put up 3,000 or 4,000, and you'll get internet everywhere all the time, which is going to be kind of good because look at all those things. But then you think, well, wait a minute. I used to go on my backpacking trip to Wyoming so that I wouldn't have to deal with the internet. Or my little around the world sailing where I'm in the middle of the Atlantic and I get a call and somebody says, hey, that software package you did last year quit. We need your help. So I'm not saying total connectivity is a wonderful thing. I'm just saying technology marches on, and it's pretty valuable for ocean and atmosphere observing. All right, so what can you do for ocean and atmosphere observing? Well, one thing you can do, as I mentioned, you can take temperature and moisture profiles, temperature precip. And by the way, that uses the navigation satellites like GPS. And then there's this what we call GNSSR, Global Navigation Satellite System, and not just GPS. There's about 100 navigation satellites that'll be up in a couple years. So you're getting an incredible amount of data. So the GNSSR, you can measure ocean or soil moisture, ocean wind, ocean waves, sea ice, and wetlands. So everywhere, all the time, with incredible real-time data. I'm not going to say much about microwave, but there's many other applications like this. I'll say a little bit about one that's particularly valuable. Here we're looking at radio occultation. The thing about radio occultation is the big expensive part of the system is the navigation system. I wonder if this shows if I point to it. Yeah, there it is. Okay, so the interesting thing is the big expensive part is this signals being generated from these navigation satellites. The signals, if you've got an orbiting satellite twice twice a circuit, it's going to sink below the horizon, and that signal from the GPS satellite is going to come through the atmosphere. It's only 100 meters high, so you have a very detailed measure of refraction. Refraction is the bending of light waves or radio waves. So you're getting a very detailed temperature and moisture. So with 100 navigation satellites up, at Spire, we already have almost 100 of our satellites up. So we're looking toward a future in 2022 where we have incredibly dense, super detailed data of temperature and moisture over the whole Earth. There's 120,000 red dots there. I haven't actually counted them, but my computer says there are. And that's an example of one sounding over the whole Earth. Here's something else. This is the NASA Cygnus satellite, which is using the same thing that I talked about that we're actually going to be testing and starting in December with our latest launch. This particular one was done by one of our scientists where we're looking at soil moisture from the reflected GNSS satellite signal. And so what you see is that, yes, the Congo rainforest is pretty wet, but there's actually wet areas in the Sahara too. Here's a beautiful picture of South America. Back in the 90s, my son and brother and I got a guide and hiked through the rainforest of the Amazon. A beautiful and fragile part of our Earth. So you see these kind of white areas. You could see one north of the Rio Negros. Those are areas where they had a recent heavy rain. So as we think about the future of Esri and what it does and our knowledge as ocean and atmosphere scientists and users, think about the cornucopia of new data that we're going to have access to understand what's happening, not just in real time, but also for climate. I couldn't do this without a view of the United States. Several really fascinating things in this picture. One of them is the Mississippi Delta is pretty wet. You might figure it is, and it is. Another thing that really stands out is the Delta. People always confuse me as a boy from Montana. What are they talking about in the Delta up way north, in Mississippi? But boy, you can sure see the old Delta, how the Mississippi from the old Western Inland Seaway, it migrated over millions of years from Cairo, Illinois, all the way down to where it is now. And you can certainly tell that. And you see all these little lakes and so on. So we have a big, beautiful, complicated planet, and we have more and new ways to look at that planet. Now I want to talk a little bit about how we are looking at that data. And ArcGIS Pro is a great place to look at data. Here we've developed what we call an optimized model in Spire. We're actually running community models like NOAA's community model and NCAR's community model, MPATH. And we're using multiple models to combine that data to get not a single estimate, but a best estimate of what the atmosphere is doing. This particular image that I'm showing is, you can kind of see Africa and South America there. It's relative humidity on ArcGIS Pro. And you see this really blue area, that's the very dry, low RH Sahara Desert. Down here in Africa South, we see the Kalahari. We see the Atacama, actually the driest desert on Earth, and the Cerrado. So in this particular thing, the red areas are the very moist areas. So it's a neat thing to be able to see the Earth as it sort of exists in geology, but in meteorology, I call it kind of fast-paced geology. Things change really fast, and you've got to have these incredible amount of data that you ingest and process in real time. Here's another product that we have have worked with on the Esri ArcGIS. I was doing the talk. You can usually tell when I did my talk because there's dates on this stuff. That was last week. And I noticed in the Arabian Sea there was a tropical cyclone. In fact, I think it turns out to be one of the strongest tropical cyclones. Now, just a quick comment that they call them cyclones in the Indian Ocean. They call them typhoons in the Pacific, the West Pacific. They call them hurricanes in the East Pacific. They're all the same beast. And this particular one was actually had winds well above 100 knots. So if Joe Pica was out there captaining the ship, I would hope he's not like one of these ships. So this is Spire data where there's two ships going right into this 100-knot tropical cyclone. And I guess the question that you're probably asking is, why are they going into a tropical cyclone? I think the answer is you've got to read a couple books. One of them is Moby Dick, and the other one is the Caine Mutiny, and then you'll figure out why captains go into tropical cyclones that could easily sink them. And it does happen. So combining different types of information. Here's our ships in real time. Here's this tropical storm in real time. Here we are looking at it. And why do we care about these things? Well, both in real time and on climate timescales, you care because you want to know and take action that is beneficial in some way. So this is the view pretty close to my house in Glendive, Montana. And there's that big, beautiful Yellowstone River of eastern Montana. And I fancied myself a weatherman when I was 15. My friends were a lot more skeptical. But one day I was asked, hey, let's go rabbit hunting in the Badlands. What's the weather going to be? And I said, well, partly cloudy, but there could be some snow. So here's pretty close to what happened. And we all almost died. We got lost in the snow. And that's actually the purpose of a weather forecast, is you do kind of want to save your life, right? Almost everybody has been in a weather situation that almost killed them. Almost everybody. Usually it's on the highway. Why am I on this highway in a whiteout with ice? And my kid's in the back seat, you're saying to yourself. So weather and climate help people. How do you make a better weather forecast? Well, we have our multi-model forecast and all of our Spire data, so we're working on that. But I want to talk about kind of the state of the art in how you portray weather data. And this is the only really nerdy slide, so just allow me to take a second on it. What we're looking at here is a probability density function. So, if you say, well, there's a 20% chance of getting a hundredth of rain today, that's not much information, especially when you think about what's going to threaten your life. So this one is a log-log diagram. And as we come over here, we say, well, what's the chance of an inch of rain? Typical day, it's pretty small. It's down in a single percent area. Now, here's a question. What's the chance that we're going to get 10 inches of rain today? Well, here in California in summer, sort of quasi-summer, it's November, still hasn't really started the winter rains yet. It's pretty low. The chances of a 10-inch rain are pretty low. In this audience, according to statistics, there are quite a few people who actually experience 10 inches of rain in one day. And in all likelihood, you notice this kind of purple that I have here between 1 and 10 inches in a day. And then I have this death zone, 10 inches to 100 inches of rain in a single day. Has it happened? Yes, it has happened. The heaviest rain in 1 billion days of weather measurements is 72 inches of rain in one day. But when you get above 10 inches of rain, it's a little bit like an 80-knot wind, relative humidity of 5%, all kinds of vegetation grown thick because it rained a lot last winter season. So for every event, you don't just want to know, is it going to have 1/100th of rain, or is the wind going to be 10 knots today? You want to know the chances that you or your loved ones are going to be threatened. So the real state-of-the-art information that we're pushing toward are these probability density functions, and we have to think, how do we display that? What do we do with that? I'll close with one more look, sort of to say I've looked at clouds from both sides now. I'm not going to sing it, so you're lucky, you're in good shape. But we do have a fabulous amount of satellite data. A lot of this from NOAA. US took the lead, and now there's geos around the world, as we saw in the Esri presentation. We actually have that in 3 dimensions in our model, and we're working toward, can we basically do Google Earth but with clouds? Can we basically tell you, not just now, but what are the clouds going to look like in 3 hours? So if you look in the lower right here, it's a prediction. This is looking east from Boulder, Colorado, where I live. And our prediction is, there's going to be a line of thunderstorms to the east. They're going to have a certain coloring. And we simulated that. And in fact, that's pretty close to what happened. Now, we can't go out very far. 3 to 6 hours is the limit. But a Google Earth with the real clouds is one of the holy grails that we're pushing toward. And you can think about how that is globally. We're not talking about one place. We're talking about anywhere on Earth. Here is a simulation. It's a simulation of a landing at the Denver airport, runway 16R. And the pilot is going to be facing the sun. It's difficult to see. He's going to come through a cloud. This is, by the way, designed for virtual reality glasses, so it looks a little weird in the contortions, but you kind of get the idea. Be able to simulate the Earth everywhere as it's really going to look, not just 3 hours from now, but 100 years from now, which is something that's really important. Some of you are going to fly home after this meeting. Here on ArcGIS Pro, we have the areas where you're likely to hit turbulence as your plane lands at your airport. There are hundreds of fields that people care about. There was literally a plane knocked out of the sky in the 1980s in Colorado Springs, Colorado, by low-level turbulence. So weather's important, climate's important. Understanding what's going to happen is important, and basically making it available to save not just our own lives, but also to make and to save our future atmosphere and ocean. Our life-friendly atmosphere and ocean requires us and our fellow human beings around the world to understand what's going to happen. So I'll mention that I'll be here today and part of tomorrow morning. Our head of product marketing could not make it, but I will be, if people are interested in what we're doing, I'll try and make his address available also. And I thank you for your time.